now that we understand what sets and elements are, and what are the basic things that we can do with sets, the different operations like union, intersection, complement, set theoretic difference, how to understand those from a logical perspective. Now it's our job to figure out how to take all of that understanding and put it into proof form. So when we want to write a proof that involves sets, what do those proofs tend to look like? How do we use all of the logical content that we learned about sets and set operations, and all the definitions that we learned with relation to sets, and integrate those all together into a coherent proof? So as I was talking about in our very first activity that we did with sets, was really targeted to getting the distinction between sets and their elements to be as clear as possible for you. Because most of the definitions that we would use in writing a proof involving sets require us not to just be at 40,000 feet and talking about the sets, but we have to get down into the sets, get our hands on an element in those sets, and use those elements to write a proof. So the shape of the kinds of proofs we're going to be talking about today, I call them element arguments. So we're going to learn today how to make an element argument to write down a proof of a set theoretic idea. And the first of those set theoretic ideas is this one from today's warm-up exercise. And it looks like this. Let's let A and B be two arbitrary sets. We want to prove that the intersection of A with B is a subset of the union of A with B. So that's the statement that we're trying to prove for today. And the hint is that in the video for today, Dr. Stahl had put together some examples, and it's the kind of argument that we need to make here follows those examples very closely. When we're trying to prove that something is a subset of something else, right? The way to do that is to unpack the definition of subset. And the definition of subset makes a logical assertion about the elements of those sets. A set A is a subset of a set B if the belonging of an element to A implies that that element also belongs to B, right? And so to prove that something is a subset of something else, we have to establish this logical if-then statement, right? If X is an element of A, then X must also be an element of B, right? And so when I talk about what an element argument is, it's applying the definitions that relate to set theory, right, to make a statement about an arbitrary element of the first set, right? If I pick an arbitrary element out of the set that we're trying to show is a subset of another set, then I need to show that that element is also an element in the larger set. So applying that back to the proof at hand. So one of the things about this particular set claim is that if you sketch out a Venn diagram for two sets A and B, you can convince yourself of this subset equality fairly quickly, right? The intersection of A with B would be this portion of the Venn diagram that A and B have in common. All right, so the intersection is this football shape here in the middle, whereas the union is the entire MasterCard logo. Right, it consists of the red circle and the green circle put together. And so from the Venn diagram, I think we can convince ourselves that if I pick any element in the intersection of A with B, then that element will also be an element of the union, which is the larger connection of these two sets together, right? So the picture is convincing, but it's not a proof, right? And so that's why we write an element argument, is so that we can take this intuition that we get from sketching out a Venn diagram and actually put it onto a firm logical foundation for what this argument can look like. Let's take a look at this assertion, that if I have three sets, A, B, and C, I want to prove that the intersection actually distributes over the union. A union with the intersection of B and C, in parentheses, is the same set as the intersection of the union of A with B and the union of A with C. So this union actually distributes over the intersection, and actually the converse is true as well. The intersection distributes over the union, which is something addition doesn't do over multiplication. So let's try and make an element argument for this. But we're going to start with a Venn diagram, just like we did before. If we have a good picture, we can sort of at least convince ourselves about why this statement should be true. So let me write down what the claim is here. It's A unioned with the intersection of B and C on the one hand, and on the other hand, it's the intersection of the union of A with B and the union of A with C. And we need to prove here that those two sets are not just there's not just a subset relationship here, but there's actually a set equality relationship happening here between these two sets. So, in this particular iteration of this problem, I've included a little hint with it that's actually just going to walk us through exactly what we want to talk about here. On the one hand, we want to use an element argument to make these establishments. But what an element argument does is it proves that one thing is a subset of another thing. But since we have an equal sign in between these two sets, we actually need to show the element argument going both directions. We need to show both that the thing on the left is a subset of the thing on the right, but also we need to show that the thing on the right is a subset of the thing on the left. It's the same as an if and only if bidirectional implication, right? Anytime you have an if and only if statement, you need to prove both the only if direction and also the if direction. And sometimes the arguments are different, but you need to establish both of them to show that the logic goes both ways. So I've outlined here what the element argument structure is going to look like for going each of those two directions. On the one hand, to show that this, the left, is a subset of this on the right, we'll pick an element in the set on the left and then try to show that it belongs to the set on the right. And then separately, so we hit the reset button, and we show the other subset inclusion by picking an arbitrary element on the right set and proving that it belongs to the set on the left. So for starters, let's see if we can understand what the union of A with the intersection of B and C would look like in my Venn diagram. So following the order of operations, I'll start with the intersection of B with C. That's going to be this football shape that B and C have in common. And if I then want to union that with A, then what I'm going to be doing is just including all of A alongside this thing that we have. Right? So the union of A with the intersection of B with C would include all of these purple shaded regions in my diagram. Right? All right, so then what about the expression that's on the other side? On the other side here, I've got an intersection of where the union of A with B, so that's the red and the blue MasterCard logo here, and the union of A with C, which is the red and green MasterCard logo, I want to know, where do those two MasterCard logos overlap one another? Right? Which portions of this Venn diagram are both in the red and blue MasterCard and also in the red and green MasterCard? And sure enough, everything in the red circle is going to belong because it belongs to both of those MasterCards. But then also everything that is in both the blue and the green are going to belong. Anything which is, let's say, anything which is in here, right? It's in B, but it's not in A or C. That's going to belong to this set, but it's not going to belong to that set. And so it won't survive in the intersection because the intersection only takes the overlaps. Similarly with the empty portion of C here. If I belong to C but I don't belong to A or B, then I'm going to belong to the union of A with C, but I'm not going to belong to the union of A with B. And so I won't survive in the intersection either. So this seems to make sense, just sort of looking at what the Venn diagram for each of these two sets would look like. So that's a good sort of reasonableness check before we embark on a proof. If we're unsure about whether the statement is true, we can convince ourselves with one of these kinds of diagrams. And when you're a working mathematician, most of what is actually interesting for you to prove are things that people don't already automatically know is true, right? Conjectures. And so, doing one of these little checks is good, just so you're not trying to chase down a statement that's false and trying to prove it, right? Because you'll probably end up hitting a wall. Okay, so let's, again, outline what the element argument would look like. We have to establish those two different claims. We have to establish that if I pick any arbitrary x belonging to A union the intersection of B with C, I then need to prove that that x belongs to the intersection of the union of A with B and the union of A with C. So that's going to be one portion of the argument. So maybe I'll use two of these napkins to do this. One for the forward argument and one for the backward argument. So stack a second one alongside it here. So how I would set up that first part of the argument is let's let x belong to the union of A with the intersection of B and C. And we're trying to conclude at the end of it that x belongs to the intersection of the unions of A with B and A with C. Right, so that's one piece of the argument that we have to make. And the other piece is exactly the converse of that argument. So for that, we need to let x be selected arbitrarily from the intersection of the unions of A with B and A with C. So A union B intersection A union C. And on that side, we want to deduce that X belongs to the union of A with the intersection of B with C. So we need to make the conclusion there. Thus, X belongs to the union of A with the intersection of B and C. So I want to walk through these arguments sort of paying specific attention to individual steps along the way, because then the activity that we have to work on in our breakouts today is actually going to give you more practice with those individual little elements, those little nuts and bolts of almost the sort of the hidden steps that a lot of proof authors will make. If you're trying to read a proof of an element argument, there are these little logical steps that authors make, but they often don't write down along the way. That can they can interfere with your ability to be successful in structuring one of these proofs. So we're going to get a ton of practice with those little steps. I'll try to call attention to them as we make them. So let's start with the one that's over here on the left. We start with, let's let X be an element of this nasty set, right? The union of A with the intersection of B and C. Probably what we want to do is take apart all of the logical content that's involved in the set operations, right? And working from the outside in, I would say that the first set operation we might focus on is the operation of union. So I'll plug in my definition of union to convert this into a more logical and less theoretical statement. So the definition of union is going to tell me that X belongs to A is one way in which X could belong to this union of two sets, but the other way in which X could belong to one of these sets is that it could belong to the other set that participates in this union. It could belong to B intersection C. Okay. So there is a step in which we are trading out a set operation for a logical operation. And what's great about that is that now that I have it as a logical operation, that gives me more structure for my proof. It gives me a simpler thing that I can assume, but it gives me sort of two different alternatives. And because there's an or here, for me as a author of this proof, I see that or, I know I have to establish that this conclusion is true no matter which one of these two alternatives happens. And so this suggests to me that we probably want to proof by cases at this point, because we don't know for sure whether X might belong to A or it might belong to the intersection of B with C. And we need this conclusion to be true in either one of those cases, so we need to establish the cases separately. So let's turn that or into a hallmark of a proof by cases. So I'll make this case 1. If X belongs to A. And case 2. If X belongs to the intersection of B with C. So I break that out into two cases, and now we have to establish each one of those two cases separately. Okay, so let's assume for the moment that X belongs to A. Maybe I imagine in my Venn diagram that my element X is here. Let's just say, right? Hopefully that won't get us into any trouble, because all we know is that X belongs to A. So it could belong to this region in the diagram, it could belong to that one, or that one. This one gives us the least assumptions, right? So we'll sort of assume that X belongs here in the Venn diagram. It belongs somewhere in A. How am I going to deduce that X belongs to the intersection of A union B with A union C? Well, let's take a step back from our conclusion that we're trying to make, as we often do, and eliminate this intersection, right, operation. Right? In order to demonstrate that X belongs to the intersection of these two sets, we need to show both that X belongs to this set and also that X belongs to that set, right? So I'm going to try to write that here. Thus, we need to show that X belongs to A union B and X belongs to A union C. So that's what we need to establish. That and is then going to become this intersection by the definition of intersection. So how do I know that X is going to belong to the union of A with B if I know that X belongs to A?
By the definition of union.
By the definition of union, exactly. If X belongs to A, then by definition of union, we know X belongs to A union B by the definition of union, but then also X belongs to the union of A with C by the definition of union, right? Any element of A will automatically get membership in A union anything, right? It doesn't matter what comes after that union. If I belong to A, I belong to the union, right? So thus, X belongs to the union of A with B, and X belongs to the union of A with C. And so, by definition of intersection, X belongs to the intersection of A union B with A union C. Right? And so case 1 is disposed of. So now that we don't have to worry about case 1, let's worry about case 2. In case 2, we make the assumption, let's suppose X belongs to the intersection of B with C. So in my Venn diagram, it belongs to one of these two areas, right? We've already proven the case where X belongs to A, so I don't actually need to worry about this area in the Venn. Let me just imagine that my X is in this area of my Venn, because that's the only region on this diagram that we haven't already proven by proving case 1. Okay. So if X belongs here, how are we going to show that it belongs to the intersection of A, of the union of A with B and A with C? So I want to make, again, that same conclusion here. Thus, X belongs to the union of A and B, and X also belongs to the union of A with C. So how am I going to know that? Well, X belongs to the intersection of B with C. What does that mean by the definition of intersection?
It belongs to both B and C.
Correct. We know X belongs to B, and also we know that X belongs to C. That's using the definition of intersection. Right? That's how we know that we can locate X somewhere here in my Venn diagram. Okay, but what is my burden of proof? I need to show that X belongs to the union of B with A and also to the union of C with A. And we know that X belongs to B and X belongs to C. Well, what is that definition? If I know that X belongs to B, how do I know that it belongs to the union of B with A?
Definition of union.
By the definition of union. And there is a complete outline of the forward implication of this proof, right? So again, we said a lot of things in this process and didn't write every single one of them down. But the key elements here in making this argument were, first of all, to establish this subset inclusion. So I'll write down underneath here, what is the statement that we actually proved? We just proved that A union with the intersection of B and C is a subset of A union B intersected with A union C. And so that's what we've written a proof of on this napkin up here. And we did it by an element argument, first selecting an arbitrary element from the set on the left of my subset equality, right? And then we have to show that that element belongs to the subset that's on the right. And the key steps along the way were completely just conversations, translations between set operations and logical operations, which are informed by the definitions of the set operations, the definitions of union and intersection in this example. We use the definition of union to split this union into a logical OR, which then bifurcated our proof into two cases, because we then had to prove both for the case where X is an element of A and also for the case where X is an element of B intersect C. That became two cases. And each one of those cases, we use the definition of union or the definition of intersection to arrive at the conclusion we were trying to arrive at. And we knew what conclusion we needed, again, by using the definition of intersection to take a step backwards. Right? In each of these cases, our burden of proof was prove that X belongs to the union of A with B, and also we have to prove that X belongs to the union of A with C. And if I establish both of those claims in each of these two cases, then I've proven everything I need to prove. The second napkin is the reverse implication. We need to prove here that A union B intersected with A union C is a subset of the union of A with the intersection of B and C. So that's what we're going to do over here. So the argument in the other direction, we begin by choosing an X which belongs to the intersection of the unions of A with B and A with C. So here the first logical operator that I would eliminate here is this intersection. First and foremost, x belongs to the intersection of two different sets. So let's eliminate this intersection first by using the definition of intersection. So the definition of intersection is going to tell me that actually two things are simultaneously true. We know that x belongs to the union of A with B, and also that x belongs to the union of A with C. So the nice thing about an AND is that it doesn't split us into two cases. We get to assume both of these things. We get to assume that x belongs to the union of A and B, and we also get to assume that x belongs to the union of A with C. So we don't have to split things into cases, probably, at least not yet. Let's take a step back from our conclusion. It's actually the same as the first step forward that we took on the other napkin to unpack this union. In order to establish this result, we need to be able to show, well, we can prove one of two things. X belongs to A, or that x belongs, to the intersection of B and C. And the great thing about this is it's kind of like we're aiming at two different targets, and as soon as we hit one of them, we're done. Right? That's the nice thing about an OR. If I can prove that x belongs to A, then we're done, and we don't have to worry about the other one. If I can prove x belongs to the intersection of B with C, then we're done, and we don't have to worry about the other case, right? So I have two different targets to aim at, and if I hit even one of those targets, then I've finished my proof. But probably those two targets are there for a reason, because we might not be able to get to the conclusion by just hitting one of them. We're going to have to hit, well, we'll see what happens as we unpack what's happening here, because I think the next step would be for us to eliminate the OR quantifiers here. Right? Because we get to assume both of these things are true, but each one of these things is a logical disjunction, right? It's an x belongs to A or x belongs to B. So we can either say x belongs to A or x belongs to B, or x belongs to B. And we can also say that x belongs to A or x belongs to C. Right? That's using the definition of union to unpack those steps. So we get to assume both of these things are true, that x belongs to A or x belongs to B, and we also get to assume that x belongs to A or x belongs to C. Let's keep that and in between here. But now this is probably a good time to take these ORs, and again, like we did before, say, well, it looks like we're going to have some cases that proceed from this, right? And in each of those situations, because we get to assume both of these things are true, one of the cases is that x belongs to A. So let's make that our first case. Case 1, if x belongs to A. Well, take a look at what we're trying to prove. We're trying to prove that either x belongs to A or x belongs to the intersection of B with C. But we have exactly hit one of those targets already. Right? If x belongs to A, then we're done. If x belongs to A, we're done. And we would just pick up right here. Okay? Because if it belongs to A, then in particular, it belongs to either A or the intersection of B with C, or both. Right? So in case 1, if x belongs to A, we don't have to worry at all. So it's the other cases where we might have a little bit more work to do. Let's make this other case x does not belong to A. So let's suppose that x is somewhere outside of my red circle. Right? So where are the possibilities? X could be where I sketched it here, but also x could be over here, or x could be over there. Right? So let's assume that we're in this situation over here. If x doesn't belong to A, then what do I know? We know that x belongs to the union of A with B. But if it doesn't belong to A, that must mean what?
That it belongs to B.
That it belongs to B. If I belong to the union, but I don't belong to one of the sets in that union, then I must belong to the other set in that union. That's called the law of disjunctive syllogism.
Wouldn't it be technically B difference A?
Yes. that is another good way to put this, right? If we want to use the language of set theoretic difference, that is what this part of the blue circle, which is outside of the red circle, would be called B minus A, right? It's that part of B which does not overlap A. So that's another way to say this. If X doesn't belong to A, then I'm going to kind of write these two assumptions here. Oops. If X doesn't belong to A, then by statement number 1 here, we know that X belongs to B minus A. As you say, yep, that's a good way to think about what we can say if we say X doesn't belong to A. Right? X belongs to the union of A with B, and so if it doesn't belong to A, it must belong to B minus A. But that's not the only assumption that we made about X. We made two assumptions about X, and this was the other one, that X belongs to A or X belongs to C. But if we assume X didn't belong to A, and it does belong to the union of A with C, that must mean X belongs to C minus A. X belongs to C minus A. Right? It belongs to that part of C which doesn't overlap A. So we know for sure from these two statements that X belongs to B because of the statement in blue here. And we also know that X belongs to C because of the statement that's in orange here. Another way to say that is to say B minus A, which is a subset of B. C minus A, which is a subset of C. Right. You see that? It's kind of right at the edge of my board here. So X belongs to B minus A, but that's a subset of B. X belongs to C minus A, but that's a subset of C. Therefore, in particular, X belongs to X belongs to B, and X belongs to C. X belongs to B, and X belongs to C. And if X belongs to B and X belongs to C, what set does X belong to? The intersection of B with C. Yep, by definition of intersection. So in case 2, we end up hitting the other target. Right? In case 1, where we assume that X belongs to A, we hit the first of the two targets. So that's why those two targets were both necessary, right? That if, in the case where X is an element of A, we're automatically done because it will belong to the union of A with anything. In the case where X doesn't belong to A, which, by the way, this is the least expensive way cognitively to get two cases. If you know what one of the cases is, just make the other case the logical negation of the first case, right? If my first case is X belongs to A, let's try making the second case X doesn't belong to A, and then see where we can get, because we know for sure that those two cases are going to exhaust all possibilities, right, by the law of the excluded middle. But then we get to the end because in one case we've proven X belongs to A, in the other case we've proven X belongs to the intersection of B with C, and therefore in any case X is going to belong to the union of A with the intersection of B and C.